Okay, welcome back in from the cold. Hope you pay attention to the words. They have some connection to this to the lecture. So today we are going to go beyond binary features, which we focused upon last week. I'll look at, for whatever better way of saying it, the type signature of fair machine learning methods is different. They're functionals of different types. I will present the gist of this particular paper, which is part of the suggested reading, and look at some connections to some old stuff in machine learning. And let's get into it. So, by the way, these pictures, each lectures different bits of Australia. This is the south coast of New South Wales. So, beyond binary. So, just to remind you what we covered last week, we introduced a couple of simple perfect fairness measures. Demographic parity requires this conditional probability is the same. Remember, y hat's the predictor, s is the sensitive attribute. And we also saw equality of opportunity, which was a different equality constraint. And because it's binary, DP also implies the same kind of relationship for p, y hat equals 0. Now, observe that if we demand that y hat is independent of s, so that's what this funny symbol means, right? The two vertical lines, then of course that's just the joint distribution decomposes, and you can just do this calculation, and lo and behold, that's just dp, right? So when we introduced dp last week, I wrote it as in the top line, but I can more compactly write it as just demanding that y hat is independent of s. Now this is very fruitful because that's going to work out nicely for random variables that are not just binary. Right? So henceforth, since it coincides in the binary case, let me take y hat independent of s as a revised definition of dp. And a similar argument, you just have to additionally condition on the event that y equals 1, suggests that we take this conditional independence statement, so that thing in blue there, you read that as y hat is independent of s conditional on y. It's a ternary relationship. If you've not met it before and you're confused, you should be. Ternary relationships are hard to grok. But we can take that as a revised definition of EO. Right? So this is nice. So now, rather than just having these big formulas to remember, right, you've got much simpler ones which are conceptually memorable. So this is our revised definition of demographic parity. And just reminding you what that means. It's just a standard definition in probability theory. So let's think of what it means in words. It means that knowledge of y hat, remember y hat is the output of our predictor, f of x. It means that y hat provides no knowledge of the sensitive feature s. No knowledge, right? I'm using that phrase in a arm-wavy sense, right? The precise definition is in terms of the independence. Likewise, the equalized odds revised definition is this conditional independent statement, which, if you write it out in full, is this big thing, right? Isn't this notation wonderful? It's much more compact. And what does that say in words? Given knowledge of the true label, y, knowledge of the predictions y hat provides no knowledge of the sensitive feature s. So there's a concrete example here. If s is sex, y is accept or reject, this would mean that predictions do not discriminate between men and women beyond whatever power these have in predicting the target variable. It's much simpler and more elegant to think in terms of the conditional independence statement. So that's just a reframing of what we saw last week, right, in a more compact way. But remember last week, as soon as I introduced perfect fairness, I said, but the world's never perfect. We need some notion of imperfect fairness. So we'd like a measure of the imperfection of fairness. And as far as I'm aware, this so far has really only been done in the binary feature case. But with this setup that I've just introduced, I'll show you now that we can easily extend that to the non-binary case. Right? So recall, again from last week, we introduced this mean difference score. So our initial requirement was that those two terms were equal. So if we measure their difference, that's a measure of how unequal they are, and that is a measure of the failure of perfect fairness. And ditto with taking this ratio. So it's whether you just, subtract or take ratios. So these formulas are in the slides from last week. How can you extend them to beyond binary? And when I say beyond binary, I want both y to be non-binary and s to be non-binary. So the thing to observe is that MD and DI are actually measures of independence. They quantify the degree to which these independent statements hold because of the development on the last couple of slides. So that's what we're doing already in the binary case. So now, to move forward, we take these as our definition, and what we're seeking is a measure of independence, right? Rather than just demanding that they are independent, we want to measure the independence. And there's several ways that you can do this. There's an obvious one, you just do this worst case thing. You just take a soup over everything and look at the absolute value of the difference. But if you imagined that y and s were non-binary and they maybe took on lots of values, you get a combinatorial explosion. And apart from anything else, it's yucky. So is there a more elegant way? Indeed there is. So what we can do is we can use one of the standard mathematical tools in machine learning and information theory, which is the mutual information. So if you've studied information theory, you would have learned that the mutual information between two random variables is a measure of dependence between them. And the definition, I've actually got the definition of classical mutual information up here. It's simply the Kullback-Leibler divergence between two distributions, right? The KL divergence, I'm hoping that you've known. I think I've got a formula shortly. It's a standard way of measuring a distance between two distributions. What are the two distributions I'm measuring the distance between? It's the joint distribution, Py hat S, and the product of the marginals. And remember the definition that y hat is independent of S. That means that Py hat S is equal to the product of the marginals. That's the definition. So if that distance was 0, then the random variables are independent. If it's not 0, then that's some measure of dependence. Thus, we could obviously demand approximate fairness by requiring that the mutual information between y hat and S is less than some epsilon. That will be a measure of approximate fairness. Now, you might say, well, you've just made this up, and indeed I have, but I've made it up based on elementary building blocks, right? Which is better than making up my own definition. But the proof will be in the pudding. We'll see that this actually leads to something quite useful. Now, as is common in probably most of the lectures in this course, as soon as I say here's a candidate thing to do, I'll tell you, no, actually, that you've got other choices that you've got to grapple with. Because it turns out, although it's far and away the most common way of doing this, when you go and define mutual information, as I have up there, using the Kullback-Leibler divergence, you could reasonably say, why Kullback-Leibler? It's certainly more common, but it turns out that there's a whole class of other measures of divergence, which you will encounter in the lecture that I won't give next week, the non-lecture, called phi divergences, or sometimes F divergences. And here's the definition here. Now, if you haven't met these before, you will not comprehend all of the aspects that I'm talking about just now, but that's why for next week, when there's not a lecture, I'm giving you some background on this so you can understand it. The way you should intuitively think about it for now is that they're just like a KL divergence, but slightly different, right? There's a different weighting function. In the case, I've given the definition here for the general phi. If you choose phi of t equals t log t, you get KL divergence, right? So the KL divergence is a special case of this. And now I can define a generalized mutual information where it's parameterized by phi. This phi has got to be a convex function and on the positive real line, and we normally require that phi of 1 equals 0. It's just a normalization condition. If we do demand phi of 1 equals 0, then we know that when the mutual information is 0 when and only when the random variables are independent. So that's pretty cool. Now, calculating this in practice is another matter, but at the moment we're just theorizing about what we should do. Now, as I said, phi t equals t log t gives you KL divergence, which is the one you're most familiar with. There's another divergence which is arguably more basic, and the proof of that claim is in the reading I'm giving you for next week. And that is when you choose phi of t is the absolute value of t minus 1. So to visualize that, it's a function on the positive real line, and it's just a v, right? It's equal to 0 at 1. When you choose that, you get a thing called the variational divergence, right? That's its name. Here's the satisfying thing, right? I said, remember originally, I started off with, dp and EO, then I said I want an approximate version of them, so we have this thing called MD, and then I said, oh, it looks like it's just a measure of independence. Now I claim that if I use this as a way of measuring the independence between those random variables with this choice, then indeed I actually get exactly MD, right? And the proof of this, it's one of these things that's extremely straightforward to check, but it might daunt you to go and look at it. So all you have to do, I've given you everything that you need, and you just have to substitute in, right? It's easy. You just do the calculation, right? I'm not going to walk through this now. This is something that you can do. It doesn't fit on one slide. You keep going, tunk, 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 tunk. And it gets bigger and bigger and bigger, then boom. Lo and behold, we've shown this. This is the bottom line, right? It's literally the bottom line of the slide. Think of what it says. This quantity, which we'd introduced in the previous lecture as a way of quantifying the degree of imperfection of fairness, turns out to be exactly this. This is very satisfying. Why is it satisfying? Because this we only defined in the binary case. This can work very generally, right? These don't even have to be scalars. They can be arbitrary vectors, right? We have this particular choice of phi. It doesn't work for other choices of phi. You might wonder why, how would you think to choose that particular choice of phi? There's a reason. This particular choice of phi has got all manner of nice properties, and the homework that I've given you for next week demonstrates that. So if probably none of you did my information theory course last year, did you? No. No matter, because I'm giving you the assignment that I gave to the information theory class to you guys, right? With the solutions, all right? So I encourage you to look at it. It was an undergraduate class, right? So you guys are master's students. This should be easy for you. Have a look at it, work it through, and you will hopefully be impressed with the result that you get, because it justifies why this is special. It links it directly to the basic loss function called the misclassification loss or 0-1 loss. Anyway, this is the first key thing, right? This is great because now we've got much more powerful machinery at our disposal to try and grapple with fairness in a more general kind of way. So what? I'm excited about this. I can't tell if anyone else is. Why am I excited about it? It suggests a better way of thinking about what MD does. I've kind of said this already. It measures the degree of statistical independence of y hat and s using a particular standard information theoretic tool. It gives a nice intuitive explanation. You want the prediction y hat to not depend upon the sensitive attribute s. Right? If you think of not depend, gets formalized as is statistically independent. Right? That's what I just said. And we acknowledge we can't achieve perfection, so we have this measure, right? So we've now got a knob, we can dial it down, and it gives an obvious generalization to the non-binary case. This certainly feels like good progress, okay? Feels like we're on the way to be able to grapple with fairness problems where we've got non-binary predictors and non-binary sensitive attributes, and it should all be nice and clean. When I worked this out, I thought I'd made great progress. This is often the way in research. You think, this is great. We're almost there. You know, we'll get ready to write it up. Oh, we'll be famous. But it doesn't actually work, right? And now I'm going to tell you why it doesn't actually work. And the reason is a little bit subtle. So it turns out, so that total variation distance, so I have implicitly defined it already for you. You can go and backtrack. I gave you the general formula for the phi divergence. I gave you the formula for the particular phi. You plug that in. It's an integral, okay? It's just an integral. It turns out, and I think this is in the assignment that I've given you, it turns out that you can rewrite it in this fashion. And this is a little surprising. What this says is that this distance between probability distributions ends up effectively being an optimization problem. It's almost like a learning problem. In fact, it is a learning problem. You've got an inf over h. H is a function from x, our feature space, into plus or minus 1. X might be quite a complicated space. So that you have to optimize over all possible functions, right? So this is hard to do. So what that means is that when you plug it into the mutual information that we demand, you've got this inf over the h. So what that means is that if you wanted to trade off approximate fairness measured in this way, like we did last week, where you've got some existing risk functional plus this penalty, you've now got this yucky min-max problem. Computationally, this is no good. It ends up being a game between a predictor and the adversary h if you think of what you would do to go and solve this. And what's going on is the function h is trying to transform the predictors so as to predict the sensitive feature, and f is seeking to make this task as hard as possible while simultaneously doing a reasonable job of predicting the target feature. Doesn't sound like I made the problem easy after all, right? You know, it looked elegant. I just measure the independence. That's all I've got to do. But to then go and put it into practice, it's a big mess. Understanding this slide, I suspect, is harder if you hadn't seen this sort of material before. But that doesn't particularly matter because all I'm justifying is abandoning this attempt, right? We're going to do something different. And the reason is that there's no real way around this optimization problem. So I briefly mentioned, certainly I think in the slides from last week, that when you couch a fairness problem as a learning problem itself, what you're trying to do is you're trying to predict as badly as possible. And you have to allow for the fact that if you have a classification problem and you get 0% error, you're doing really well. If you have a classification problem and you get 100% error, is that good or bad? Who thinks that's bad? It's good. Why is it good? You flip the sign, exactly. You've got to keep that into account, right? So we did that kind of manually in the cost of fairness paper, and it's just that flip. In this case, you have, yes, so in that case, that's all you've got to do. You just flip. For general action spaces, for general predictions, and for general sensitive features, you end up with an uncountable infinity. It just blows up. The binary case is lovely and simple. It doesn't just get a little bit worse, it gets stupendously worse. And there's no getting around it. Like you think, oh, you know, I've made a lot of choices here. Can I repair this? The bottom line is that this approach, in my view, is doomed, right? For anything other than binary, which is very frustrating because it was looking good. So that's disappointing. And Aditya and I were kind of despondent for several months. We thought we'd cracked this, and then we realized we hadn't. And then we started to think, what's going on? So behind the use of conditional independence to define notions of fairness, there lies a subtle but important presumption. And let's spell that out really explicitly. The data are samples from a stable probability distribution, since statistical dependence can only be defined in that case. Now, there are many other subtleties with conditional independence. I'll give you some references if you want to read about that. And we're going to return to the presumption of stable distributions later on in the course. But essentially, the further we looked at this, we found computational headaches, we found conceptual philosophical headaches. And so then we thought, maybe the problem, maybe the error, as it were, was on line 1, essentially. That was that we were using independence as the way of capturing no adverse effect. It's very tempting, right? You don't want the sex of the candidate to influence whether or not they get the job. That's an independence-like requirement. But we can't make it work. So what can we do instead? We can start with a different approach that doesn't start with independence. And in order to do that, we need to take utilities more seriously. In order to do that, I want to make this distinction about what I've called, for want of a better phrase, type signatures of fair machine learning methods. So here I've made this table, and what I'm trying to get across here is we have our data, the stuff that's given to us, and then we go and build an algorithm, a machine, right, which looks at certain aspects of the data. And the question is, what aspects of the data does your machine look at? So the first line I've just called fairness blind machine learning. This is just standard supervised learning case. We have our X's, we have our Y's. There's a loss function, so on the right-hand side, these are the knobs that you've got, and you've got a hypothesis class, okay? So that's an abstraction of a large class of supervised learning problems. H is your model class. We will meet in lecture 4 a thing that goes under the name of individual fairness that does not require sensitive attributes, and it tries to encode the moral principle that similar people should be treated similarly. Right? We'll elaborate that in lecture 4. In order to do that, you have to have a notion of similarity. And that ends up being this function d. Basically, it's a distance, right? X, remember, is the feature vector. So for each of you, I've got a feature vector. And then I say, I measure some notion of similarity. That could be anything. Height, age, sex, hair color, hair length, right? Program of study, whatever. I abstract all of that, encode it in the function d. We've also got the L and the H, of course. The ones that we've already met are independence-based, right? They take, there's 3 data, X, Y, and S, the sensitive attribute. And then we need this complicated functional that maps from our sensitive feature space, some probability measure. This is what we've already been looking at. But what I want to now flag is that there's a quite different way of doing this, and that's this last one. This last one is what we're looking at now. I know this looks complicated, but look at the left-hand side. What's the difference between the far left in green and the line above it? There's an X, a Y, and an S, right? And there's a loss function floating around. But the point, what I'm trying to get across here is that there's a distinction between demanding fairness when I get to see the X's and demanding fairness when I get to see f of X, or demanding fairness when all I get to see is the losses. It's what the algorithm gets to see. So it's type signature. What do you feed in to your fairness requirement? These ones, aligned with terminology in social welfare theory, I'm calling welfarist. The point is, what I'm going to do now is, in order to judge fairness, I'm not going to pay attention to the actual values of the X's or the actual values of the Y's. I'm just going to pay attention to how well I can predict them. Okay? I'm not claiming this is better. I'm simply asserting that it's different, and we'll see that we get a quite different solution that has many attractive features. And so to do this, we're leaning on this idea of utilities. And you can read about this as Wikipedia pages on utilities. This is Daniel Bernoulli. The idea of utilities came from thinking about the value of money. If you've only got $1 and I offer to give you $1, that's better than if you've already got $1,000 and I give you $1. Right? So there's this notion that the value of a given quantum of money is not just inherent in the quantum of money, right? So there's some utility associated with the person. When we talk about loss functions in machine learning, we can think of them, there's two distinctions between utilities and loss functions. The economists, when they talk about utility, more utility is better. In machine learning, more loss is worse. That's just a sign flip, right? The second distinction is that in machine learning, our utilities are outcome contingent. So normally we write a loss function, right? We have a predictor P and we have an outcome Y. And we write L of P, comma Y. Fix Y. Then you've effectively got a disutility for the prediction P. It tells you how bad that predictor P is. You choose a different Y, you've got a different disutility. So in a mouthful, you could say loss functions are outcome contingent disutilities. Right? That's the connection. Anyway, and this notion of doing your reasoning in terms of utilities rather than, say, the raw material is a big thread of work in social welfare theory. So if you were looking at, like if you're a social planner working out how much money each person should get, maybe you're designing a tax rule, right? You know, does everyone pay the same dollar amount of tax or the same percentage amount of tax? Or some more complicated thing in between. So there's lots of folks that study this. Amartya Sen won the Nobel Prize in Economics for his work in social welfare theory, and that I'm pinching from him this notion of welfarist way of thinking about things. Now, there's a lot behind this way of thinking, and so those of you who've been exposed to some philosophy, you might realize that this utilitarian approach or this welfarist approach is what's called consequentialist. It just tries to quantify everything. I've argued already that what we're interested in is translating certain ethical principles or desires into machine learning systems. Machine learning systems run on maths. So at some point you've got to build that bridge. So at the moment, our current proposal is that we work in that utilitarian fashion, right? And the logic is what I've written up here, right? If you've accurately captured what matters to you in solving a learning problem by the utilities, then all questions of distribution and equity should be solely in terms of the utility values and not the raw data. Otherwise, you should go back and design better loss functions, right? That's not a proof, it's a premise, right? It's a premise of what comes next, right? There's many other ways of approaching the fairness problem other than that which I'm presenting you, but I'm trying to be as explicit as I can about the presumptions behind mine. So all we're going to look at is this, right? The loss our predictor makes on a particular sample. So that's the gist of this paper that's in the readings for this lecture called Fairness Risk Measures. I already said this about outcome contingent utility. Sorry, I forgot I had this slide. So I was quoting this before without the symbols up there. But just to set the notation, this is standard, right? A is our action space. That's what we predict. Y is the label. Actually, I've reversed the order from what I said a moment ago. Sorry about that. So this thing here is an outcome contingent utility. Actually, it's an outcome contingent disutility because of the sign convention that we normally operate with. And our normal goal in solving a machine learning problem, this is an abstract version of a supervised learning problem. I hope you've seen before. We have some hypothesis class. We minimize the expected value of our predictor. Right? And in practice, we do it on finite samples. But hopefully you've seen that before. There's nothing special here. This is just a reminder and a warm-up. Now, just one thing on this. So it's true, much machine learning starts with the loss function and tries to explicitly fit itself into that frame, that expected risk minimization. But there's plenty of folks that would deny that's what you should do. They would rather say, look, what we're trying to do is to just get the information out of the data. Right? We want to observe the data and extract the information. Maybe combine it with our prior knowledge, so we've updated our information. Does that ring a bell to anyone? Right? So this is the Bayesian ethos. Right? Now, very famous Bayesian statistician, Maurice de Groot, in 1961, said this: the distinction sometimes made between decision problems, that's like with a loss function, and problems in which the experimenter simply wants to gain knowledge may not be very sharp. That is a monumental understatement, because what he actually showed in a formal way is that any sensible measure of the amount of information that you might extract from an experiment must be quantifiable in terms of loss functions. Right? It's a result that many contemporary colleagues still don't like to hear, I think. So I've pointed you to that. The argument's actually quite simple, but this is what he actually showed. And just to give you some intuition behind it, let's suppose we go along with your precept, that what you are doing is just getting information from the experiment. And suppose that is all that you do. Well, so what? You're enlightened, but you haven't changed the world in any way. Why do you want to get information from your experiment? Because you then want to go and do something, right? Otherwise, you're just sitting there. And as soon as you do something, it has consequences, and you can measure the effect of those consequences, so there's a loss function under the hood. He essentially makes this argument, right? So this slide's just an aside for those of you who think, oh, this whole loss function thing, it's barking up the wrong tree. All we're trying to do is to get information out of the data. Anyway, I buy into this statement, and it doesn't really matter in the sense that there are plenty of problems where there is a loss function under the hood, and let's have a think about what we do in that case. So now what I want to show you is how we might modify our standard approach to minimizing the expected loss to impose an additional fairness constraint. So here's a simple machine learning problem. It's particularly simple. I've got 10 data points, and I've got a model class. It's a nice small model class. It's only got 5 hypotheses. Okay? So with hypothesis F1, I go and compute the individual loss on each data point, and I've plotted them there. Okay? That's all that I've done. All right? And now we start our big machine learning algorithm engine that starts to optimize. What does optimize mean? We look at all of the different possible hypotheses, and we want to try and pick the best one. So let's have a look, right? Right, we choose F2, we choose F3, right? The numbers fly all around the place, and it turns out, lo and behold, F5 looks really good, right? Remember, bigger is worse, right? These are disutilities. So if that was your model class, this seems like a good hypothesis. But what have we done there? What have we done when we've said, oh, this looks good? Implicitly, I think what most of us would be doing is that we would say, we've made the average loss small. And indeed, F5, out of all of the 5 Fs that we had, has the smallest average loss, right? That horizontal line is just the average height of those bars, right? So when we're doing empirical risk minimization, what we're doing is to choose the F so that this orange line is as low as possible. Very good. Let's do it again. What's the difference? It's in color, right? What does the color represent? These represent people who come with blue, green, or red skin. Okay? Very strange country, 3 different skin colors. We do the same thing. We get the same answer, except it's now in color. All right? But now we say, what if I rearrange the horizontal axis? Note the permuted order of indices here. It's the same data. I'm going to run the same thing again. This is an experiment to see how many times I can show you the same thing before you balk. Right? So I run the algorithm again. And big surprise, F5 is still the smallest one, because if I've commuted things, the average doesn't change. But we've gone and done that, and then a journalist comes along and says, you've optimized it, but I go and do this. if I go and compute the conditional average for the blue people, the red people, and the green people, I conclude that whilst your hypothesis is good on average, the green people are paying the price for that. You'll see that? And the blue people are benefiting. The average risk for blue is smaller than the average risk for red, is smaller than the average risk for green. Now that's inevitable when you've got these bars of different height, right, generically. So now we can see a way of intuiting some notion of fairness. There's no independence here, right? We're just using our standard learning algorithm, but what we've done is we've introduced the sensitive attribute, right? We've looked at things in colour. So what can we do in that case? Well, we observe that what we care about here, right, in the way I've gone and coloured it, we don't actually care about, individual number 3, 5, or 9. Our judgment here, like in all group-based fairness, is solely in terms of group membership. We don't care whether it's Mary, John, or Priscilla, right? It's just whether their skin is green. The average loss for green people, red and blue, is not the same. So what we could do now is we could, I've just re-indexed, and we have a think about this, just an abstraction of what's going on. Inside each big green bar here, I've got all of the individuals, I'm hiding them, right? Under the hood, I'm computing the average of all of them. And I can go and do the same calculation again, and I still get F5 as the smallest, right? I've just done, if I have an average over a certain number of items, I can average over the reds, over the greens, over the blues, paying attention to how many reds, greens, and blues there are. This is just the law of iterated expectations. I get the same thing, right? So again, I've got the same solution on the same data, I'm just representing it a different way. But now, hopefully, it's kind of clear to you what you might do instead, right? Here, we've just taken for granted, because it's the normal way of doing it, that the thing to do is to minimize the average, right? That's what we've done. We've minimized the average risk. But the problem is, when we perceive the fairness violation, is that there's a variation, right? We've got to keep two things in mind, right? Implicitly, we want two things. We want it small on average, and the variation we also want small, right? It's a mixture of the two. So what might we do? Instead of having this hypothesis, F5, and I've just changed the scale here, right, just to make it more obvious, we might do a trade-off. So instead of this hypothesis, this is F5, and you look at where its mean is, because that's what we were judging, and you look at the deviation, we might say, you know what? We might be happier with that. That's a trade-off. You see, the average went up, but the deviation went down. Last week, we introduced this notion of the cost of fairness. I argued that generically, you will pay a price. Here, we're seeing that we're paying a price. So that idea that I've just presented with moving colour blobs, right, we can formalize that. We have a sensitive feature, and it doesn't matter how many there are. That's just the number of buckets that we put things into. So we think of this thing RF. We're going to have these random variables that are indexed by F. Remember, we optimize over F. So we have to carry that around. We're going to view that as a random variable in this fashion, and it's essentially just the conditional expectation of the loss conditioned on the sensitive attribute, like I said before. Rather than the average across the sample, I do the average over the reds, the average over the greens, the average over the blues, right? So we've got a family of random variables indexed by F. And normally what we would do is we would just minimize that, right? I can just compute the average in this indirect fashion by first averaging red, green, and then blue, and then averaging those three numbers. I could do that. Or I could demand some additional penalty term, a deviation penalty, something that measures like the length of that orange arrow, at least, not necessarily literally, but captures that notion of variation. So let's think about the attractive features of this proposal. So it reduces, to the standard case, I've already said that. The prediction space is arbitrary, right? We don't touch it because we don't see it. We're only looking at the loss values. We don't even need the sensitive features to be determinate, right? This is a subtlety, but which I won't explain just now. It automatically deals with a whole stack of issues such as imbalance in the relative preponderance of the sensitive features. It can deal with an arbitrary number and complexity of sensitive attributes. It's just a more complex set S. The same definition works. And if we had an easy learning problem to start with, easy in the sense that I had a convex optimization problem, then if this thing ends up being, then the resulting thing ends up being convex. I'll demonstrate that in the next few slides. So all we need is some sensible measure of fairness. Right? This is a new measure of fairness. It's going to be something that jointly measures the average and some deviation term. It pays attention to both in some nice kind of way. So that's what we want. So now we're in the situation where we see we want some functional. We could just make one up, right? I could just take the difference, like the height of that orange arrow. But it's good to work out all the possibilities and then choose, hopefully, the best one. And the nice feature of this line of thinking is that most of the work was already done, right? So we start to do this. We say these are the axioms that we want. Lo and behold, someone's already invented what we were after, and we can just use it without any great work. So that's very nice. So in the next few points, I'm going to give you the requirements that I impose in two different ways: the formal definition mathematically and also a justification. And this is spelt out in the paper that I've pointed you to. There's an appendix where we kind of argue why these axioms are good. Remember, you can't prove axioms. By definition, axioms are the things that you choose not to prove, but you can ask for a justification of them. So convexity is certainly nice mathematically, right, and for writing computer programs, but it also has a nice ethical interpretation, namely that you can't reduce the risk by more fine-grained partitioning. Suppose that the red people, you could segment them into light red and dark red. If you do more fine-grained partitioning, then life does not get worse. That's the argument, right? Slightly subtle, but that's in the appendix of the paper. Positive homogeneity, this is a mathematical convenience, but I think you can argue ethically why it's a good thing to do. Expectation is positively homogeneous, meaning simply E of C times X is C of E times X, where C is some constant, right? It scales. So it's like a preservation of units, right? It's like if you convert everything from dollars into cents and then back again, your solution doesn't matter. It's just a change of units, right? The expectation is positively homogeneous, so we'd like our functional to be as well. We'd like monotonicity. This is a kind of a minimal requirement. We wouldn't like it to be the case that the more deviation that we got, the worse, the better we claimed people were off. There's a technical continuity condition that, again, you can argue ethically that this makes sense in terms of small changes in the solution should have small changes in the effect. I realise that's a bit of a stretch, but it ends up not mattering enormously. It's just technically very nice to have. And this thing here with the fancy name translation equivariance, the expectation has this property. Z is a random variable, C is a constant, and you would like this. What this means is that if you think of this in terms of money, if you give everybody an extra $1, nothing changes, right? Again, it's a desirable thing to have. And the final one is aversity. That is that these quantities are always worse than the expectation, a larger value in that sense, right? That actually accords with our intuition when we were looking at these quantities that just because we've got a small expectation, because there's a deviation, we say, no, there's a penalty there. You're paying a price for the deviation. And then the final one, this does seem a little opaque and hard to wrap your head around, but I explain it in simple words. There's a distinction between a random variable and the distribution that the random variable has. Implicitly, in most of the work we do in machine learning, we just elide this. We always think in terms of distributions, right? We never actually think of the numbers that we get. We're always thinking that they're samples from a distribution, and we would like to be able to do our maths in terms of the distributions, right? That's got a technical name. It's called law invariance. It only depends upon the probability law, right? Two random variables with the same distribution will be treated in the same fashion. Or the other way to think of it is the only thing we pay attention to is the distribution, right? For many folks, it's kind of like, well, duh, we always do that, right? But it turns out if you want to be careful, you want to write down all of the assumptions that you're actually making. Anyway, so we did not dream up these names or indeed the axioms themselves. It turns out that there's a long line of work going back 20 years or more in mathematical finance where these things have been used. And they're respectively called coherent or regular measures of risk according to which set of axioms they satisfy. These things are very widely used. The central banks in Europe are regulated using these kind of measures, right? They use it to measure the volatility of portfolios and so on. So same kind of notion, right? If you think, you've got a bank, it's got a bunch of assets, but you care about how much things jiggle around, they've been motivated for the same reason. And some of the literature that I point you to, you'll see that. You'll see the logic, that financial logic behind it. Anyway, it turns out, this is great, all of that stuff is pre-existing. We don't actually have to do any great work. We just steal it. We just take these regular measures of risk on which there's lots of papers telling you how to compute them, all sorts of properties, and just apply them to our problem. And it really does capture the answer that we're after, right? So this thing that we thought we wanted, some way of measuring the fairness of our problem, we can always write it in this form here. So they have all these nice properties. You can always write your fairness risk measure as a sum. Like, it's not obvious that it's always a sum. I said we'd think of it as adding a penalty term. It turns out you always can do this. And that these deviation measures, they have nice properties too, very similar to the ones on the previous slides. There's some examples there. The expectation is indeed one of them. The maximum, formally it's called the essential supremum. If you allow for continuous random variables, you have to take account of measure zero events, but essentially it's the max. And in essence, all of these measures live between the average and the max. So go back to the toy example with the red, green, and blue, and just think about what that would look like if instead of taking the average loss across each person, I took the maximum loss. Right? Just have a think about what that would look like. We're going to come back to that later on. And there's one that we're going to explore in a little more detail today, which has got a fancy and opaque name called the conditional value at risk. And it's defined simply like this. Z is a random variable. Q alpha of Z is the alphth quantile of Z. So if alpha equals 0.5, it's the median. Right? Alpha is 0.75, it's the upper quartile. So it's the upper tail. If you visualize the distribution of the random variable, we're looking at the upper tail. So if we pick some alpha, say alpha equals 0.75, then C var alpha of Z, we just take the top quarter of the numbers that we've got and we average them. So in that toy example I was showing you, we would not pay attention to the loss that the bottom three quarters got because it's less than what we've already got. So what we're doing is we're paying more attention to the samples on which we're predicting worse. And it's very much like the ethical principle. I don't care how much money everyone's got in detail, but I find who's poorest and make sure that they've got enough to eat. right? And maybe I give them some money. But we don't, you know, if you've already got plenty of money, we don't look after you. So there's a nice ethical interpretation of that. This family is particularly nice because as you adjust the knob alpha between 0 and 1, you interpolate between the smallest and largest risk measure. So it's this one parameter family that gives you a wide range of behavior. You set alpha equals 0, you've got standard empirical risk minimization. You set alpha equal to 1, you are paying all of your attention to the worst off. Anyway, it turns out, so this looks completely different to the stuff that I'd previously shown you, right? There was no conditional independence. I didn't start with, you know, those existing measures, disparate impact, equality of opportunity. But it turns out if you then go and check, are they related at all? And so here I just skip over that a little quickly. If you just now take one of these risk measures, the particular one that I've said there, and you apply it in the binary case, then lo and behold, you find that the natural measure that we already had to measure the imperfect fairness in the conditional probability, in the conditional independence setup, can be expressed in terms of the absolute difference between these two random variables here, which is what's captured by the SD risk measure. So I know that's a bit much to absorb in one go. All I'm saying is that this different, seemingly very different way of codifying our desire for fairness ends up in the particular cases that work with conditional independence, namely the binary case, they're effectively the same anyway, right? So this kind of justifies it. This is satisfying. And this idea of when you invent a new thing, you want to go and check how it relates to the old thing is a fine thing, right? It's good if it reduces to the old thing rather than being something completely different. Anyway, the idea is not completely crazy. And the one thing we can then do with this, which I think is very cool, so one of the things I'll talk about at length in a later lecture, in the group-based fairness setup, right? So we can go and say we can have sex, or we can have race, or we can have wealth. Depending upon which groups that you choose, you'll get very different answers. Of course you will, right? And what if you didn't want to have to choose the groups? Well, that's the beautiful thing about this, right? We've got people of every skin color here. Everyone's a different colored skin. We can deal with that. We can do our optimization in the same way that we were doing before, and then we will choose, not according to an average, but again, we'll just look at the deviation. So there's a way of imposing fairness on these predictive solutions that completely ignores what category that you're in, but nevertheless is imposing some kind of fairness notion, right? If you have one of these fairness measures other than expectation, you will ensure that there are not people that have a terribly high error. Anyway, so that seems nice because it just sidesteps the whole problem of groups. Does it solve everything? No, right? I'm just telling you what it does do. All right. So essentially what you've done here, so does anyone know this guy? You're all too young. This is Vladimir Vatnik. Maybe you've heard of the Vatnik-Chervonenkis dimension if you've done the learning theory course. But he's the guy who formalized this principle, minimize the empirical risk, right? That's his, I'm very proud of this photo. I took the photo, right? This was actually in Tübingen in 2012. Anyway, so instead of minimizing empirical risk, you just replace the expectation functional by something else, which has almost all the same properties as expectation. And most of your algorithms continue to work just fine, but in addition, you've imposed a fairness constraint. It's like a different inductive principle. That's what he says. So this R, you can think of it as like a nonlinear expectation. Anyway, time for a short break. Just 5 minutes, please.
Ich bin gestern ein bisschen unsicher, ich bin schon untergegangen. Bei dem Regen auch. Ja. Offensichtlich. Ja, ist noch hier. Wie viele Kinder hast du?
About the lecture.
Sorry?
Can I ask a question about the lecture?
Yes.
So you mentioned in the beginning you had this adversarial game between minimizing the
Yep.
So in this case you want to minimize the mutual information.
Yes.
So what instead of minimizing you sort of set constrain it and then you can use the dual problem and then the adversariality is not exactly explicit. How would that affect the game?
So there's many, so look, the issue is not whether you can set it up as this game. The complaint is simply that computationally it becomes a pain in the neck. That's all. So, I mean, if you can solve it, it's fine, right? I mean, I think it's like on ethical grounds, it's very well argued that this is a fine thing to do, right? It's capturing just what you want. It's just that it's a bug of the work, right? So that's.
I think so. Yeah, it's a very real work because of adversarial game, like the minimax.
Yes.
So if you try to use the dual problem, then you sort of you add another like parameter, the real multiplier that then the minimax is against this and not between the measurement.
No, I understand. It's still. My recollection is we looked at this and we hoped that yes, by going to the dual. So oftentimes you go to the dual problem and it becomes trapped. That's not the case here. That's at least my recollection, right? But I wouldn't swear to that, right? It was. Yeah. I mean, the reason I'm mentioning that is to give a bit of a story as to why go back and try something completely different, right? And to be completely different, you have to start quite a different spot. Yeah. I think we talk about this in the Fans Risk Mission paper. There is a slightly elaborated argument about this. Okay.
Also ich habe einen Smartphone benutzt, so ich habe Laufing vielleicht läuft ihr dann Füller. Ja, aber ich habe mir halt extra neu geholt und das ist sofort wieder passiert. Das ist irgendwie die Art, wie ich den halte. Ja. Da gibt es Cookies, aber hast du auch einen Ort für alles, oder? Nee, das ist sehr viel. Ich habe den größten für den Tag genommen, weil ich jetzt nie muss ich am meisten machen. Hier laufen halt für so 10 Jahre am meisten.
Ich habe auch nur so ein Schnellheft.
Ja, auch ein iPad 6 wahrscheinlich.
Ja, ich höre noch ein paar Stichwörter, aber der wollte ich gar nicht mit, weil ja. Aber ich will jetzt jetzt schauen, ne? Das war viel, das ist ja nur ein Länderbeschau.
Okay, we'll carry on. So, just briefly on this strange thing called conditional value at risk, it looks bizarre. Remember, it's the conditional expectation of your random variable given that it exceeds the alpha quantile. So one quite surprising thing, which I discovered after the fact. So at first sight, this looks quite unusual and exotic and a weird thing to introduce into machine learning. 20 or 25 years ago, there was a class of machine learning algorithms called support vector machines. Has anyone heard of them? A few. Good, they're not that old, right? And they're still used. Anyway, it turns out, this is a big surprise, you can derive the support vector machine by using the conditional value at risk. So in a single line at the top there, the objective function in the SVM, you can express in terms of CVAR. Now, I'm not going to try and develop that for you. It's like a lot of steps, and I'm pointing you to a couple of papers that illustrate this. But if you understand about how the SVM works, it should not be enormously surprising because the SVM solution ends up just depending upon a small number of support vectors. it kind of ignores everything else, and its solution is controlled by just those. Normally the way you think of it is the points closest to the decision margin, right? Even in the non-separable case, the argument still kind of works. Anyway, there's a parameterization of the SVM called the nu parameterization, the Greek letter nu, and that nu basically controls the fraction of your data points that are support vectors. It ends up that it just pops up here in terms of this CVAR parameter. So if you know about SVMs and you have some intuition about them, then it might be worthwhile looking into this to kind of make you more comfortable with this functional that I've introduced, which I'm now going to lean on a lot, right? So I said before that it's used, there's other kind of algorithms that use it as well, that you can look it up. Yeah, so the idea of using a non-linear version of an expectation is not actually that weird, right? Because we'd already done it without realizing it. When it was originally developed, people did not derive it in this fashion. It was something that was observed only afterwards. Another issue, which again, I'm simply just going to give you the formula and you can look this up if you have a particular interest in it. To compute CVAR, it can be a pain in the neck, particularly for discrete random variables, because quantiles end up being set valued. I'll mention that again shortly. It turns out that you can always express CVAR in this form here. Why this is true is not obvious. It would take me a while to work that through. In the paper, we give you some references for it, but this is nice. So this thing with the plus, do I say? Yes, it's just the positive part. So it's just an expectation. And this is just a one-dimensional optimization over a single real parameter. And so if you had a problem that was already convex when you're minimizing with expected risk, so you've got an n-dimensional model class, so n's 1,000 or something rather, and you've got your optimizer working all very nicely. If you want to modify it with this fairness objective by swapping out the average with CVAR, all it amounts to is jacking up the dimension by 1. Right, because you just now have a convex optimization problem in 1,001 dimensions. You just augment the parameter with this row, right? Easy peasy. It doesn't really cost you anything. So that's nice, right? But I'm not expecting you to be able to figure out why this is the case, but you can play with it, like, on your computer if you want. And then in our paper, there's some experiments where we use that. So there's a nice, so this CVAR is nice, but it's still just one parameter family. It's natural to ask, is there something richer? Like, as soon as if you just think of ordinary functions that you learn in high school, so you can learn about linear functions, right? They've got a straight line as a graph. And then you've got non-linear functions. They're all other functions that don't have a straight line. So in some sense, which you can actually make precise, there's a lot more non-linear functions than there are linear. Likewise, there's a lot more of these non-linear expectations than there are the traditional linear ones. So we're going to just get a little bit of intuition about that, right? So it's really just one bit of insight to, make you feel a little more comfortable with using a non-linear average, because at first sight, like you've had 10 years of practice taking the normal linear average, it's kind of weird to use these things. So just some notation. So most of this is standard, like the cumulative distribution. I said that you have to, with discrete random variables, quantiles are a pain in the neck because you can have the lower and the upper quantile. You have to pay attention to whether you've got strict inequality. This is yucky to go through in a lecture. I just want to assert you need to pay attention to that. I'm going to gloss over it, but if you want to do things carefully, you've got to pay attention to it. So in general, if you want to say the quantile, it's not a number, it's an interval, right? In many cases, it reduces to a single number. Right, so we gloss over that. Anyway, so it turns out, this is not that hard to show, given the definition that I gave you, that you can express CVAR as this weighted integral of the quantile function, right? So this is the tau quantile, and I integrate tau from alpha to 1 and weight it by 1 over 1 minus alpha. That gives you some intuition. Like if I had my random variable, I've got its cumulative distribution, I invert that, I get the quantiles. right? I then integrate the quantiles over a certain range. That is CVAR, right? We demanded that these things are law invariant. They only depend upon the distribution. Therefore, there must be a formula for the thing that we want in terms of the distribution. Here it is, right? Here's one of them. There's several different ones. But then what you can do is you can say, well, suppose you've now got a choice. Like this is a point I'll reiterate many times in this course. If I just choose alpha equals 0, that's the average. If I choose alpha equals 1, that's the max. I don't know, I might not know what alpha to choose. In fact, I might want to hedge between them. What if I take a linear combination? I take CVAR alpha equals 0.5 and CVAR alpha equals 0.7, and I average them together. Is that okay? It turns out that it is, and you can do that systematically in this fashion here, where we've just made a weighted integral of CVAR alpha according to some weighting measure lambda. Now these things have a name, right? And these are things that were developed in the finance community, and they're called spectral risk measures, right? And I guess the word spectral, it's nothing to do with light or anything. It's a risk spectrum, right? You think of lambda in terms of a density on the unit interval. It's how much weight you put on different values of alpha. You pick any sensible density alpha, then this thing R sub lambda is a legitimate risk functional to use for our purposes. And there's various transformations you can do on that. I'm not going to you can read the slides because I really just want to get to the next slide to show you some intuition. It turns out you can check these are coherent. I defined coherent on the slide with all of those axioms. Remember? I said coherent risk measures are the ones that satisfy these axioms. So these are perfectly good to use for our purposes. And they have an interesting interpretation that might be helpful to give you some intuition about what's going on. So first thing is we can rewrite the standard expectation of a random variable in this fashion. And if we now go and pick some non-decreasing function phi, let's just think of the distorted expectation. So here I'm making something up. Like this is kind of weird. If phi was just the identity function, I get the traditional expectation, but it's like I'm distorting things, right? It's literally called a distorted expectation. This quantity was developed in the insurance literature, independently of all the other stuff that I've told you about. And it turns out, and it's only a few steps, and I encourage you to try and work through this. It's essentially just a change of variable in integrals. It turns out that every distortion, this guy, is equal to one of these spectral risk measures, right? And there's an explicit relationship between the parameter, the phi and the gamma. So I introduced this general family with this parameter gamma, right, which was this function, right? That's how you tune your risk functional. I can equally well tune my nonlinear distortion, right? For all sorts of reasons. The insurance people had, risk aversion reasons for doing that. It turns out that they're the same thing. What's the big deal about that? The fact that you can get to the same quantity from different perspectives is always a good clue that it's an interesting quantity, right? It's not just something that you made up. The fact that it's related to other attempts for people to try and capture notions of equity, like in insurance, tells you that you're on maybe even a better track, right? And I'm not going to mention it in any detail, but since, people have worked this out, I've observed that these same objects that we're looking at, you can derive them from about 8 different starting points. They're a very natural class of quantities to use when we're dealing with data in the way that we want. Anyway, so look, the bottom line here is simply that this strange new quantity that I introduced, you can think of it as just a distorted expectation, which is kind of satisfying. I said it was a nonlinear expectation. Right, so this notion of imposing fairness and worrying about inequity between people, this is not a new idea, as I've already alluded. And there have been many attempts from very different disciplines to grapple with it. And one of them is from economics, right? So economists have worried about this a lot. right? Do you end up with a society with a few billionaires and everybody else is starving, right? You need some way of quantifying that. So, you know, I've already flagged that our subject is interesting because of this combination of needing to do things mathematically and worrying about ethical concerns. The economists have realized this as well. So these are essentially a set of quotes that I found. The sources are in a footnote in the paper. Economics is essentially a moral science, whatever the protestations to the contrary by some of its practitioners. Economic science must merge with moral science, right? Anyway, they're all kind of saying the same thing, but these are all different people, right? They come to the same conclusion. The most interesting one I want to dwell on for a little bit is the following. This is by Anthony Atkinson, who did a lot of the fundamental work on measures of inequality. And let's look at this. Many of the ambiguities and disagreements in economics stem not from differences of view about how the economy works, but about the criteria to be applied when making judgments. People can legitimately reach different conclusions because they apply different theories of justice. That's what we're doing in this course, right? As I go on and on about, there's no single right way to judge these questions. So as engineers or technologists, whatever you want to call yourself, you have to be able to handle all of them, right? To understand the implications, at least to make the consequences of the choice manifest. That ethos sits behind a large line of work in economics on measuring economic inequality. And you've probably encountered this already. There's often newspaper articles that will say, you know, worldwide economic inequality continues to increase, right? You know, it sometimes goes up, it sometimes goes down. But what does it even mean, right? How on earth do you even define it? Well, that's the subject matter of that we're talking about here. Now, it turns out, so where am I heading with this? It turns out that what the economists do when they try to measure inequality ends up effectively being the same thing as what I've just proposed to you. It's not obvious that it's the same. It's in disguise. And to unwrap the disguise, we've got to harmonise the notation. And this is a good exercise for you to see, because it's often the case where here you are working in this discipline, you think you might want to go and pinch some insights from over here, and everything about it is different. Even the most basic notation is different. So you've got to build a dictionary to translate everything across. So that's what I've had to do here in the next couple of slides. So they don't talk about random variables and distributions, they talk about people, right? They index them like this. We've got x1 to x2. They represent n people in some way, perhaps their income. And then an inequality measure is just a function, right? We take everybody's income, glom it together somehow, and come up with another number that measures the inequality. Now, all I've done there is to give you the type signature of the function, right? I mean, it could be the constant function. That's kind of useless. So, but at least I've told you what it eats and what it spits out. In order to spell out what properties that we might like, we need a little bit of notation. So one of the key things that matters here is not how much money each person has, but it's the distribution of it, right? What you care about, who's the richest person, who's the poorest person. So to that end, they use this notation, which is not unusual, for just sorting the incomes. So I measure everybody's income here, I get all of these numbers, and then I sort them into decreasing order, right? And I'll always just work with that, right? Because I don't care, right? From this perspective, I don't care who's the poorest, I'm just interested in the distribution. So that's just the notation for decreasing rearrangement. So it has this formal property. And then there's this important notion that this crops up in a lot of mathematics called majorization. We introduced this partial order relationship between vectors in this fashion here, right? Where, remember, the square subscripts on the x's, that's this notation up here. This is the ith largest income. We've sorted everything in decreasing order. So x subscript square bracket I is the ith largest income. So if we have this condition holding, then we say, X dominates Y in this sense, in the majorization ordering. I realize that just looking at these formulas for the first time here, that won't mean much to you. I think that's the most complicated thing I'm going to no, it's the second most complicated thing I'm going to show you. So we can then build upon that. So here, like I said, I reiterate, I'm doing a translation exercise of the arcane terminology that this other field uses, right? You're comfortable with your little area of turf of machine learning, you know all of these things. You go and talk to an economist, they'll say, what on earth is that? What's a dropout regularizer? And you'll think, everyone knows what a dropout regularizer is. Same thing, you dive into economics, they'll use this terminology and you think, I have no idea what they mean. You work through it, it's not that hard, right? Shear convexity is just a weakening of normal convexity. If a function is convex, it's guaranteed to be shear convex. It's defined in this fashion here, right? If X dominates Y in the majorization ordering, then that implies 5X is less than or equal to 5Y. That's the property of phi being shear convex. I would be astonished if you have a good intuition about this at the moment. It's just a formal definition. For the sake of what I'm about to tell you, just think of it as, oh, it's like convexity, but not quite. That will do, right? And yes, there's the connection with normal convexity. Every convex symmetric function is shear convex. Now, we need this because one of the most classic ways of measuring economic inequality, and this is the one that would be quoted in newspapers, builds on a thing called the Lorentz curve. And so, again, there's just some standard notation that we need. So there's nothing hopefully new to you there except my choice of notation. You know what a probability distribution, a cumulative distribution, and its quantile or quasi-inverse is. And then we go and define these quantities here, right? This is the crucial one. And you might think this seems reminiscent of the CVAR formula I gave you a few slides ago. I'm just partially integrating the quantile. That's all that I'm doing, right? Main takeaway is that these things are just defined in terms of the standard quantities. I started with a bunch of numbers. I then think of them as samples from a distribution. I then use the machinery of distributions, including quantiles, and I can go and define this quantity L. And then there is this thing called the Lorentz curve, right? So this is a curve. I realize I haven't drawn it, but hopefully you can visualize this, right? This is an ordered pair on the plane. P goes over the unit interval, right? So that's your horizontal axis is P. And then we plot Lx of P, right? It's just the graph of Lx of P.
I think there's a parenthesis missing.
There is a parenthesis missing. Thank you. Just there. Yeah, thanks. I never spotted that. So all this funny terminology, this is what you'll see if you go and read, a summary of economic inequality. There's ways of ordering numbers, and I'm going to skip that because you can read this later on. What I want to get to is to just show you, not so that you can absorb as I go, but you can look back when I get to my punchline. You can then go back and look at these things and say, this kind of makes sense. So there's references that I've given you that say, here's the way people think about economic inequality. And precisely because, depending upon your choice of inequality measure, you'll get different answers. People try to approach it systematically. Like you can imagine politicians of different persuasions wanting to use different formulas. So this goes back 100 years, and so people have tried really quite hard to pin down what are natural ways of measuring inequality. So I've written them up here. I've given them in a formal way. I believe my slides are fully self-contained given the brief notation that I put up earlier. And I've also tried, like I did before, given the ethical interpretation. So let's just look at some of them without necessarily absorbing all of them. So one which I think most people would argue would be symmetry. It shouldn't matter how I index people, right? We're looking at the population as a whole. Scale invariance. So this one's a little different. We're trying to measure inequality rather than overall wealth. So if we double everybody's money, then the inequality should not change, right? The idea is, what these people were after was they just wanted a measure of inequality, not a measure of welfare. More funny terminology. If this function is strictly Schur-convex, for 100 years they've said that this satisfied the Pigot-Dalton principle. You can see I had to do a lot of digging to understand this. This has got a nice interpretation ethically, right? This is why it's 100 years old. If income is transferred from a rich to a poor person in a mean-preserving manner, then inequality cannot increase. So they're thinking in terms of how you would use these things for wealth redistribution. We've measured the inequality. We now go and take $10 from the rich person and we give it to some poor people. Mean preserving means that the person doing the transfer doesn't pocket any, right? $10 from the rich person, I give a $1 each to all of the poor people, right? Intuitively, we think that's good, and so we demand that our measure of inequality doesn't get worse. Right? That's what it says. There's another one, the Dalton population principle. If a finite population is replicated, then the inequality will not change. I take all of you, I clone you and your bank accounts, and then have a double-sized class, measure the inequality on that, it should be the same. There's some normalization. We add a constant, it doesn't change things. We want it consistent with the Lorenz ordering, so that's harder to justify. Then there's some ridiculously complicated ones, which I'm not even going to go through, but just to show you, these guys, they've had 50 years to develop this, right? Anyway, it goes on and on. I've only given you a subset of them. Seriously, right? But with all of that, right, I want to get to the punchline. I'm nearing the end of the lecture. It turns out that all of this stuff, which is, well studied and, used for government policy and, a lot of attention's paid to it, is that there's a direct connection between it and these risk measures that I was talking about in the first half of the lecture. And you have to do this bridge. Like I presented the inequality measure in the way the economists do. They say we've got x1 up to xn is a bunch of people. In machine learning, we think in terms of random variables. That's easy. I just think of a random variable on a sample space which is discrete. I can match this up in a formal way. And we also know that this is a key point with our risk measures, right? I said this, but I want to say it again. This is an important theorem. Every one of these risk measures, every regular measure of risk, satisfying that set of axioms that I demanded, always can be written as a sum of an expectation plus this function, this deviation functional. Why is that significant? It means that I can either choose R, and then of course D is a derived quantity, D is just R minus C, or I can choose D, and then R is a derived quantity, right? I don't choose both R and D, right? It's just a different choice of parameterization. And that matters in what's coming, because what I now do, and here is the new insight, and this I think is actually quite simple and gives insight that, as far as I could tell, no economists had realized, is that you do the following. You start with one of these Ds, right? I gave you some examples on the previous slide, and now I go and define this new functional I, right? It depends upon D. D's fixed, I define I, and I do it in this fashion here. Ignoring the case when the expected value is 0, I just normalize it by the expectation, right? So all I've done is just define a new functional. Now, equivalently, I can invert this, of course, and I can just say, equivalently, I could say, instead of using D, if I wanted to use R, remember I said I could use either, I can pull the same trick here, right? I get from this to this just by appealing to that. It doesn't matter. So I can either say I sub D or I sub R. And I can invert both of them, right? This one here, given a D, I get an I, or given an I get a D. Nothing complicated, right? All I've done so far is define stuff, right? I haven't actually shown anything. But Here's the interesting thing. If R satisfies my earlier axioms, F1 to F7, then IR satisfies these inequality axioms that I showed you just a couple of slides ago. And conversely, if I satisfies those, then RF satisfies these ones, right? The logic is slightly complicated. What this means is that you can start with your regular measure of risk, and then these inequality measures just come out from this normalization. You take your regular measure of risk, you subtract the expectation, you're left with the deviation measure, you divide by the expectation, lo and behold, that's a measure of economic inequality. And you recover a lot of this work that people have done for many decades. But I would argue that the monotonicity property, which is very nice for our risk measures, it's invisible to the inequality measures. So the inequality measure, one of the axioms was if I double everybody's income, the inequality measure doesn't change. With our risk measures, they're positively homogeneous, right? So in mathematical terms, the inequality measures are zero homogeneous. Anyway, so what? What it means is that we can derive many, but not all, of the measures of economic inequality from these risk measures. So if we were kind of concerned that, look, it seemed a little arbitrary, like my motivation for introducing them was, well, I tried to do this thing with conditional independence, so it didn't work, so I went back to the drawing board, and this kind of worked. But now we realize that, look, in disguise, once you reparameterize it and realize the distinction between just worrying about inequality and welfare, right? Inequality is that everyone's got the same income. Welfare is both everyone's roughly equally well off and you're all on average well off, right? Those two, if you keep that distinction in mind, then we've reduced one to the other, right? Which seems to me a fairly compelling argument why these fairness risk measures should be paid attention to. So what? It's interesting to learn from other disciplines. Methodologically, I don't know how much you've been exposed to this way of thinking in your previous courses, but here we are trying to do this new thing, right? So this whole question of how do you make machine learning ethical? You can just go at it head on. I'll dream up this measure, I'll come up with an algorithm, I'll try it on his benchmark data set, here are my results, right? There's lots of papers like that. And then next week, you'll do the same. You'll dream up one. You'll get slightly different numbers. It won't be directly comparable. You all end up doing that. And then eventually you think, what is the point, right? You don't learn much from that. So what instead I'm trying to do is to reduce things to the bare minimum, right? Where you say, rather than just dreaming up some new thing, as soon as I've dreamt up a new thing, I try and relate it to as many old things as possible to see how well it aligns. And the more connections I can make, the solider the building is. So that's a methodological trick, which I'm a big fan of. All those axioms, I know I went through them at light speed and you could not have absorbed them in a single sitting, but I do hope you go back and look at them. But I want to tell you why I want you to look at them. I'm not asking you to memorize them because there's no quiz, right? The reason for doing this axiomatic approach is not to derive the one true way of doing things, it's to understand the implications of what you're doing, right? So you've come up with this particular inequality measure, you like it for all sorts of reasons. Checking which axioms that it satisfies helps you understand the ethical presumptions that you have made, right? Like the first one, that the ordering of people should not matter. That seems pretty fundamental, right? Like it shouldn't matter who was first in the door. Anyway, so that's another kind of methodological point. And yes, I've said it in different words here. It's not like, this is worth saying explicitly, you will find in some literatures where people, I think, quite mistakenly reckon that because they've started with these axioms and they've done this logically valid reasoning, they end up with a proof that this is the right thing to do. I'm not claiming that, right? right? I keep stressing that actually there's lots of choices here. With these risk measures, there was many different risk measures that satisfied the axioms. We've also seen, I've already made this point, inequality is not quite what we want in machine learning. And there is if you're really keen, you could compare this paper to the fairness risk measures paper. In essence, what they did what Aditya and I did, except they used inequality measures. And technically it ends up being a gigantic mess. It's just yucky because they're using these zero homogeneous functions. They lose convexity. They have to do all of these hacks, right? We set it up, I think, in the nice parameterization where it's easy peasy, right? You just swap this one thing out, plug it in, bam, it all works. So that's off, you can often have the same idea, but you go about it in a slightly different way. I think this is a terrible way of doing it. So we're done. So what did we do today? We saw a quite different way of ensuring fairness, which has the additional value of showing yet another way, right? It's not just we had the two that I introduced last week. This is a completely different class of ways of imposing fairness. It has this quite distinct way of doing it, that it doesn't pay attention to the x's and the y's or the f in your problem. It only pays attention to loss values. It can work on arbitrary groups. You don't even need the sensitive attributes. It's related to the SVM, and what we just saw is that strong connections to the measures of economic inequality. So that's it for today. Thank you.